Hello. So what we are going to do next is we are going to try how to implement a neural network with a very popular neural network library called Keras. So you can install that library. The installation instructions are available online, and I'll be posting a link to those. And it's a really cool library that allows you to create neural networks, multi-layer perceptrons, convolution neural networks, all types of neural networks with it's essentially a very few lines of code. So what we are going to do is we are going to solve the same classification problem that we have solved earlier using bare bones PyTorch, and we are going to port it over to using Keras. Okay, and what we are going to do is we're going to have this our good old plotted function that allows us to visualize the scene boundaries. So we're gonna just go through it, like you don't need to make any changes. Just like any good machine learning problem, all you need to have is a matrix of your features. Each row is a feature, each column, each row is an example, each column is a feature. In this case, we have 1, 2, 3, and 4 examples in two-dimensional space. You can have higher dimensional examples, and you can have more number of examples for a given problem. And for each of them, we are given a prediction label. Y in this case, for the first example, that is -1, 0. The label is -1. The second example is also a negative example, and then we've got two positive examples. And what we are going to do is that we are going to make a neural network, a very simple neural network with only two neurons in the hidden layer. Now, it's really important to understand that the structure that we've been studying of neural networks, so we have two input features which are going to form our input neurons. Now, each of those neurons are going to be connected to the neurons in the hidden layer, and so each of those hidden layer neurons accepts then two features as input, which is written over here. Each neuron takes two inputs, the two features, and the output of the two neurons is fed to a single output neuron. Because we have a single output requirement for this, for each example, we are producing a single output. Therefore, we need only one neuron in the output layer. Okay. If we need more than one neurons, we can add more than one outputs. There's another very important point, and that's a common rookie mistake. We can have different type of activation functions, as we've talked about in the theory part of this lecture, or developing neural networks, right? That of a single neuron in the input layer does not have any activation function. It simply passes what the feature it's getting onto the next layer. The hidden layer has an activation function. It can be a rectified linear activation function. It can be a sigmoid activation function. It can be any other activation function. And then we have an output layer neuron, which can have its own activation function. Now, the fundamental requirement of an activation function in the output layer is that it should have enough dynamic range that it should be able to produce any target values that we want it to produce. Let's say if I have a requirement that I need to produce a value of -1 for all of my negative class examples and a value of +1 for all of my positive class examples, then I need to make sure that the activation function that I'm applying on the output layer neuron is able to do that. Let's say if I use a rectified linear function there, because I know a rectified linear activation function produces a value of 0 or larger. It's not able to produce negative numbers, so a rectified linear function will not be a good choice here. Either I need to change the input labels from these bipolar targets, which are -1 and +1, to simply 0 and 1, in which case I can go ahead and use that. Okay, and it's really important to make sure that the dynamic range of your targets coincides with the dynamic range of your activation function in the output layer. Okay, so what we are going to do here, we are going to use an MSE, or the mean square error, as the loss function, and we are going to do back propagation. The good thing about Keras is we don't need to work out all of those nasties or nasty weight updates, and it's a really smooth experience, right? So let's go ahead and make the neural network. So from Keras, models import sequential. Since the neural network that we are going to talk about are sequential neural networks, in the sense that they are feed-forward neural networks. So the input of this layer feeds into the next layer. So there is a sequence there. That's why this is called a sequential model. So we initialize an empty model, an empty neural network, and then we add neurons. And since our neurons are going to be connected, all neurons in one layer are going to be connected to all neurons in the next layer. So this is what a fully connected neural network is. That's why it's called dense. So we're going to make a dense layer of weights that has two inputs. There are two neurons, there are two features. That's why this is 2. And this over here is 2. We are going to make we're going to add two hidden layer neurons. That's what we have said over here. So that's where this 2 comes from. And because each of those neurons is going to have 2 features, which is the number of features in my example over here, that's why this input dimension is set to 2. I'm going to initialize the weights of this neural network, or by specifying init is equal to uniform, is going to initialize the initial weights of this neural network prior to backpropagation in a completely uniformly random manner. So that's what this does. And I apply the activation function called ReLU, or rectified linear activation function, at this hidden layer. So that is, we have added 1 layer. Okay. And the next thing I need to add is simply, I need to add another dense layer. So each of the hidden layer neurons is going to be connected to the next one. And that's what we are going to do over here. So we add a single neuron, which has a fully connected structure with previous neurons in the previous hidden layer. And we don't need to specify the input dimension for this one. Keras automatically figures it out when we add it like this. So we just need to specify the uniform over here, and note that I've specified linear activation over here. And the reason for that is because I need to produce these -1 numbers. If I use ReLU over here, it will not be able to do that. And you can verify that by simply by making that change. Now, the good thing about this is when I say model.compile, and I specify a loss function in there, which is going to be the mean square error loss. You can also specify other loss functions. And you only need to specify an optimizer, which I've done in this case. So this is a more refined version, or an improved version of gradient descent called ADAM. So it's adaptive momentum-based gradient descent. You can also use classical gradient descent by specifying that as an optimizer. And then you can specify what type of matrix you want to calculate, such as accuracy or anything like that. And once I call this statement, then I don't need to worry about calculating those derivatives by hand or anything like that. Okay, so it's easier in certain ways in comparison to what we had done in PyTorch or what we had done by hand in our lecture notes. And all I need to do training is I need to specify my training data, which is X with the corresponding labels Y. I need to specify how many epochs I need to do. So an epoch, remember, is how many optimization steps over the whole of the data set does the neural network need to do in order to learn. So in this case, since we have only 4 examples, I'm specifying 1000 epochs. So what's going to happen is, in the backpropagation algorithm at the back end of this, the Keras library is going to take a data point, one of the data points in my data set is going to perform or it's going to do a weight update for one input that I specify in or the whole of the training data set that I've specified in my in this X variable over here, and the corresponding labels in Y, and it's going to do those weight updates 1000 times over for each of these for all the examples in my data set. So just to make it a bit more clear, we have a data set, and the number of epochs is how many times does the neural network look at the data that I have when it's trying to optimize itself. So specifying an epoch number equal to 1000 means that when the neural network is trying to update its weights, it's going to look at my data set 1000 times. So each of the 4 examples is going to be looked at 1000 times as well. Now this is interesting. We can have a batch size which we can set equal to 4. So if you have a very large data set, it's possible that we'll not be able to fit all of that data set at one time into memory. So what we can do is to pick a small batch of that size of 4, which coincides with the number of my examples. So what I'm saying is, dear neural network, take all of the data, 4 examples, at once and compute the weight update over all of those 4 examples. You can specify different numbers here. You can specify 3. If I had specified 3, then it would have chosen 3 out of 4 examples at one time, performed a weight update on that, then pick the next in a cyclic manner, pick the next 3 and so on, until I've seen or I've gone through all of the data set 1000 times. So when you call this model.fit, you need to specify how many epochs you want to have, what's the batch size you want to have. Since the data set is really small, I'm going to fit all of the data set at once by specifying the batch size equal to the number of examples. Okay, we're going to have a bit more discussion on the impact of this batch size parameter. In certain cases, you can get better optimization properties by specifying more larger batch size. Okay, and in some cases, a smaller batch size is more useful or does quicker convergence. So let's say we have got these 1,000 epochs. So this is what it's going to do. At each of those epochs, it's going to look at all of those 4 examples once I execute this code, and then it's going to print out what's the loss value. So this is the mean square error loss, and it's going to print whatever metric I've specified, that is accuracy in this case. So how many times do the predictions match the targets that I've specified? So the accuracy at the beginning is 0 and the loss is pretty high. But as we go through these optimization steps, you notice that the loss value keeps on decreasing, but the accuracy is still 0 until quite late. So you can scroll through all of this. The loss is decreasing and your accuracy is now improving. It's 25%. So one of the examples is being correctly classified. We can continue doing this until we converge. So the loss is almost 0 now and the accuracy is 100% over the training data set. Now that doesn't necessarily mean that it's a good network on a given test set, but we're not going to worry about generalization just yet. We just want to understand how neural network backpropagation works in Keras, right? So now once we have all the neural network has been trained, once it has gone through all of those 1,000 epochs, I can generate predictions from my trained neural network by using its predict function. And in this case, it's going to spit out the prediction scores for each of those examples. The first example generates a prediction score of minus 1.22, the second one minus 0.53, the third one 0.89, and the fourth one 0.86. Remember, the first 2 examples were negative, the last 2 examples were positive, so this is correct classification with a threshold of 0. And we can of course plot the decision boundary over here, which is done over here. Okay, so that's how you can make a very simple neural network or fully connected or a multi-layer perceptron in Keras without worrying about anything. It's pretty easy.